Well, we're going to now commence our second session of the morning, and it's my pleasure to introduce and welcome to the stage Dr. Rudolph Staudigl, I apologize for the mispronunciation, who is the President and CEO of WACKER CHEMIE. Please join me in welcoming Mr. Staudigl. Thank you.
Your Excellencies, ladies and gentlemen, thank you for giving WACKER the opportunity to present today. Changing, adapting, renewing is important. It certainly is not only important for our company. Every long-term successful company had to go through variations or various changes. Otherwise, it wouldn't exist anymore. In our case, we look back to more than 100 years. The company went through many changes, many phases of external upsets, but also significant internal changes. Many products were divested over the years, like PVC, chlorohydrocarbons, fibers, and so on. There were others that have been newly developed and modified. There were joint ventures that have been formed and dissolved. The key always was to tackle the challenges right away and not to postpone them. The key is the willingness for the whole organization to change. WACKER is a $6 billion in sales company. Our business portfolio is based on 5 divisions. All divisions have leading market positions as number 1, 2, or 3 in their respective markets. Over the last 15 years, we have set up a global footprint for all divisions. Our 3 chemical divisions, Biosolutions, Polymers, and Silicones, are 65% of sales. They have grown 7% on the average over the last 10 years. 25% of our business is carbon-based and 75% is silicon-based. We serve a wide range of applications and industries like pharmaceuticals, food, construction chemicals, automotive, solar materials, all the way to silicon wafers for semiconductors. Let's look at our carbon-based businesses before we turn to the silicon industries. Our, what we call polymer products, are primarily serve industries like construction, adhesives, paints, carpets, and so on. They are made by copolymerization of vinyl acetate and ethylene. They are adjusted to their application by the copolymer ratio. Vinyl acetate is rather hard and tough, whereas ethylene is rather soft and flexible. The right mixture, also adjusted by the addition of other monomers, steers the properties to what the customers need. Very hard types, for example, are used for top coat systems. Soft types are used, for example, for so-called engineered fabrics. The products can be delivered either as dispersions or redispersible powders. Growth rates of the respective markets are slightly above GDP for dispersions and at least 2 times GDP for powders. The market drivers are increase of productivity in construction, higher building standards, as well as improvement of quality of life in general. Let's move to biotechnology. It's our second carbon-based division. We have started to develop this division by developing a genetically modified E. coli bacteria to produce the amino acid cysteine in high quantities. The beauty of the modification is that the bacteria enclose the product into a little bubble and move it out of the cell, where it can be harvested. Traditional technologies actually do not have the advantage of forming these bubbles. So when E. coli bacteria produce some materials, you basically have to open the bacteria, kill the bacteria in order to receive the products. So basically you kill the cow to get the milk. And our technology exactly avoids that. So we were also able to modify the bacteria so that they can also make human antibody fragments for pharmaceutical applications, so-called therapeutic proteins. Not only that, another development gives us the opportunity to adjust the folding of the proteins so that they can be more readily used as pharmaceutical products. We have strengthened our technological capabilities also by small acquisitions as well. Of course, these complex molecules could never be made by a chemist in the lab. Therefore, I'm convinced that biological capabilities will be more and more needed for leading-edge specialty chemical products and companies. For substances made from microbial applications, we see growth rates of 2 to 3 times GDP. And in my opinion, only the use of microbial and enzyme technologies will enable us in the future to develop the use of renewable resources as feedstocks for materials for everyday life. Now let me turn to the silicon-based chemical industry. It is a big word, from sand to quality of life. But if you look in which product silicon is found, I think everyone will agree. There are not very many companies active in this industry. Besides our company, these are Dow and Momentive in the US, Shin-Etsu in Japan, Blue Star and GCL in China, and OCI in Korea. In all modesty, I can say none of these companies has such a complete silicon portfolio as WACKER. Of course, like in many industries, there are very many small Chinese players who are not internationally active and technologically not competitive. Now let me give you a quick overview of the most important products and aspects in this industry. It always starts with sand, or better quartz, and the final products are very high purity polycrystalline material that is turned into semiconductor or solar wafers. Second, silicone polymer products for multiple applications in a wide range of industries. Let's talk about polycrystalline silicon first. You start with quartz, silicon dioxide again, make metallurgical grade silicon. Then metallurgical grade silicon is reacted with hydrogen chloride to make trichlorosilane. Trichlorosilane is refined to a hyperpure product through distillation and is then decomposed on the hydrogen atmosphere to hyperpure polycrystalline silicon. Hyperpure means 11 to 12 N. So 99 point and then 9 N's more, or 10. It's a very energy intensive process. So energy price is important for the cost position and thus competitiveness. The respective chemistry sounds simple, but the aggressiveness of the involved chemicals requires extensive know-how. The processes need to be run in closed-loop systems since all involved chemicals are highly sensitive to air and moisture. The total market size is around $6.5 to $7 billion. Volume demand growth is in the 2 times GDP range because of the growth of the solar industry. However, past demand growth, which was in the 20% range, has triggered very significant overcapacities, mainly by new market entrants. But a new market player simply is not able to reach the very demanding quality levels of the semiconductor and latest technology solar applications. Therefore, there is substantial overcapacity for lower grade material in the world. Upgrade of the quality level is very capital and know-how intensive. Ultimately, only the high quality suppliers will survive. The market for polysilicon for semiconductor wafers is with $1.5 billion fairly small, but feeds into a $7.5 billion wafer market. On these wafers, companies like Intel, Samsung, Toshiba, Micron Technology produce memory and processor chips. On the $7.5 billion wafer market, a $300 billion chip market is based. And the whole electronic industry is founded on this technology. Since the semiconductor industry is continuously progressing, the material requirements are becoming more stringent all the time. I give you an example. The flatness of these wafers is such that when you imagine a wafer spread out through the whole equator of the Earth, the highest elevation that is tolerable is 3 meters. Or you can imagine the area of Saudi Arabia, for example, and the highest elevation is a few centimeters that is tolerated. As a leading-edge supplier to the semiconductor industry, it is important to ever improve the material parameters while you reduce cost continuously. A strong cost position and reliable quality can only be reached by a very high automation level. For quite some time, there was a significant overcapacity in the world for leading-edge 300 millimeter wafers. Now we are at a crossover point where demand becomes higher than available capacity. You can see that in the stock price appreciation of the respective companies, including our own subsidiary Siltronic, of which 42% is traded on the stock market. Let's talk about the biggest user of polycrystalline silicon, the photovoltaic industry. More than 90% of modules are based on silicon. To produce solar modules, you start with polycrystalline silicon. From the raw material, you either grow multicrystalline ingots or monocrystalline ingots. The ingots are sliced into wafers. The solar cells are made on the wafers. Then the cells are assembled to modules that later are mounted on rooftops or on fields in order to produce renewable electricity. The development of the solar industry will be textbook knowledge in Harvard courses in the future. Why is that? To make a long story short, the installation of solar modules was so over-subsidized in Europe first. It grew so fast that a polycrystalline silicon shortage developed. Prices went from around $30 per kilogram to more than $400 per kilogram. Then everybody invested in huge capacities, even companies who didn't have any technology. Therefore, the price level collapsed to $10 to $20 per kilogram. Even low-grade material could be sold because demand was just so excessive. The same became true for every segment of the value chain. Overcapacities everywhere. This, in turn, fueled price reductions in the whole chain so that solar has become very competitive. Recent investments in Abu Dhabi, for example, sell power for 2.7 cents per kilowatt hour. The market for polycrystalline silicon grew to $6.5 to $7 billion. The solar module market grew to over $35 billion annually. Annual power installations amount to around 70 gigawatt. Because of this tremendously fast growth of this industry, there's a lot of imbalance in the supply chain. Therefore, we will see lots of consolidation and specialization in the industry over the years to come. Only world-scale, low-cost players in each sector will survive independently. And even the integrated players will need to be world-scale and world-competitive in each and every segment of the value chain. All this will ultimately drive the cost of solar further down. So cost reductions are a necessary trend as well as further technological improvements. My prediction is that monocrystalline ingot growth will grow much faster than multi, providing for higher efficiencies and thus lower electricity costs for consumers. These technological trends towards monocrystalline wafers and cells need highest purity silicon. Therefore, capacity for highest purity is not available in excess, but can only be produced by experienced market players with the respective know-how. Highest purity is not only increasing the efficiency of solar cells, it also decreases variability, which is shown in the middle graph. This in turn means more revenue for the producers of cells, modules, and electricity. In terms of multicrystalline wafers, there is, in my opinion, only one technology that I can imagine to ultimately be competitive. It is when you cut out the wafering step from the production sequence. A startup company in the US has established a pilot production which shows very promising results. This is why we invested in this startup. It is called 1366 Technologies. The name stems from the amount of solar irradiation on the Earth. Of course, they are working with our highest purity material. Now I would like to come from hyperpure silicon to the chemistry of silicones. As already mentioned in the beginning, silicones are important products in our portfolio with a wide range of applications. The chemistry of silicones is built by large-scale upstream processes for siloxane and downstream processes to make silicones with special properties. With upstream siloxane, we see a highly competitive market characterized by capital intensity, overcapacities in China, and constant cost pressure. For downstream silicones, we see continuous growth opportunities for specialties. The main trend is the innovation and creation of customized properties by modification of chain length, ligand type, 2- and 3-dimensional structures of molecules, and use of additives or fillers. The combination of a leading cost position upstream and a customized portfolio downstream is needed to capture above GDP growth. Besides specialties and innovation, one key to success in these industries lies in highly integrated production facilities, a so-called Verbund system or closed-loop chemical system. We run 2 of these in Germany and 1 in China. With our integrated sites, we can produce in a most efficient way for lowest cost and a minimum of undesirable byproducts. In this picture, you can see that silicones and polysilicon are produced with a very similar raw material base. Energy recycling and closed chemical loops make the difference in terms of cost efficiency and contribute to the sustainability performance. We also gain fumed silica as a highly value-added byproduct, which can be used in many industries. At the same time, we find synergies not only in the production setup, but also in regard to personnel and expertise within our company. You might also call it a know-how Verbund. But as you can see, even if the chemical formulas look simple, the Verbund is built by significant assets and it takes significant capital to create it. Over the last decade, we invested substantially to build our global assets upstream and downstream in Germany and China to support our growth today. And we just finished our polysilicon plant with a closed-loop infrastructure in Tennessee that can be used as the next so-called Verbund site in the United States. So-called silicone downstream products are true specialty chemistry products. Basic requirements for these type of materials are a solid world-class asset base that is run with operational excellence. But this is not enough. The recipe for success lies in customer focus and continuous innovation. What means customer focus in specialties? It means a global footprint in application technology. It means local know-how in R&D. It means local customer support teams. What means innovation? In a nutshell, it means to provide specialty materials that can be adjusted to various changing needs of customers. For silicones chemistry, I have already mentioned the variability through chain length, ligand reactivity, structure, and additives. Nowadays, most of the innovation in product application has to take place at the overlap of specialty chemistry with other industry segments. I would like to demonstrate this on 3 short examples of innovation projects. The first example is at the overlap between engineering and specialty chemistry. 3D printing in silicones business opens up new applications and opportunities. Target segments are prototyping in general, but especially in the medical industry, all the way to personalized medical solutions. First printers are running with enormous interest by many different industries. It is known from material science that the storage capacity for lithium is about 10 times higher in silicon than in carbon or graphite. It could lead to a tremendous advantage in battery development. This is important for storage of renewable energy as well as for electromobility, where lithium is used as an electrolyte. And electromobility only makes sense, of course, if the energy is generated renewably and not through combustion of gasoline or coal. We have developed a silicon anode system that shows very significant improvement compared to graphite. It is now under testing at a few selected battery producers. Last but not least, this example combines material expertise in silicones with biotechnology. The target application is a microalgae farm. Microalgae convert sun power and carbon dioxide into biomass. Biomass can be used for food application in general or to gain special nutrition products. In the right setup, algae provide the potential to produce biomaterial in large scale on a totally renewable basis. An algae-based bioreactor has been developed in an optimal setup to capture sunlight efficiently and make optimal temperature control possible. The reactor tubes have to be highly durable and provide for very low algae adhesion. All these requirements are fulfilled by concentrically extruded hoses of specialty silicone elastomer. We have not yet found any other material which is superior to silicones. In summary, I hope I could show you that silicon is an important material for modern life. First, as an element in its high purity form, multicrystalline or monocrystalline. Especially products in the form of silicones, which are highly adjustable to serve in many uses of modern life. Flexibility, adaptability of technology is needed to make innovations possible. Innovations based on existing technologies and chemistries have become more important than the invention of new molecules. Thank you very much.